My name is Hayes, a technical designer and gameplay engineer from Utah, and today I want to walk through my recent graphics programming work in OpenGL. I was recently able to implement a highly performant, multi-scale screen space ambient occlusion solution based off the research of Duong and Kok-Lim, whose work I've linked in the video description. For those who are unfamiliar, ambient occlusion is a 3D rendering method intended to simulate the effects of true global illumination, basically real-life lighting, wherein crowded spaces appear darker in their creases and crevices due to light scattering. However, true ambient occlusion is still highly demanding on performance, as it requires ray tracing in order to calculate a shaded value for each point in your scene. Thus, screen space ambient occlusion was born, a kind of approximation of an approximation that captures the visual features of true AO while being significantly easier on performance and implementation. Screen space AO, as the name suggests, calculates an AO value for each fragment in the screen, basically a pixel, rather than actual 3D points in space. It uses kind of a similar G-buffer approach as deferred rendering, making it a great companion for the deferred rendering workflow. A standard SSAO implementation follows a fairly simple set of steps. First, we do a geometry pass, drawing all of the objects in our scene into the G-buffer and storing their position and depth values into a texture. Basically, we're taking note of the position of every object in the scene and their distance from the camera so that we can fully draw them later on and storing these sort of blueprints to create these objects into a texture. Next, we do the AO pass, rendering a screen space quad with normalized device coordinates. Basically, for each fragment, which again is kind of a pixel on the screen, we are testing random depth values within a sample hemisphere kernel of that fragment's stored texture position. We're going to use this to calculate an AO factor. Basically, we're taking a look at the space around this fragment's stored position to see how crowded it is with other mesh objects. We need to do this a lot of times to get good-looking results, with the standard being 64 random samples per fragment. This occlusion factor is then stored into a texture as well. Next, we need to do the blurring pass. This is important because standard screen space ambient occlusion creates noticeable banding artifacts around objects, and it looks very artificial. By averaging each fragment's occlusion factor based on the surrounding fragments, we're kind of able to eliminate this banding by blurring the whole result, storing an updated occlusion factor into a texture. It's important to note that we are not blurring the entire scene, but rather just what the occlusion is going to look like in that final scene. Finally, we're going to do a lighting pass. We render another screen space quad to the screen, draw all of our objects, and light them using a blend-fong model. All we have to do now is multiply each fragment's ambient color by the occlusion factor, ensuring that a high AO factor for a fragment results in a darker overall fragment while still taking into account its lighting and coloring. Now, screen space AO is amazing, but it does have some noticeable drawbacks. While being very fast, its results are not always high quality, with the banding as mentioned before, which requires an expensive blurring operation to resolve. This brings us to multi-scale ambient occlusion, my beloved. When fully implemented as seen in the Duong and Kok-Lim paper, this solution is a massive improvement over naive SSAO in both performance and visual quality. They accomplish this by altering how sampling kernels work. With naive SSAO, a single hemisphere is used for each sampling kernel, with the random points within this hemisphere sampled X many times to calculate the occlusion factor. Multi-scale screen space ambient occlusion splits this up into 3 unique sampling spaces. So we have kind of a close-range hemisphere for objects that are very close to the tested fragment, a mid-range hemisphere, and also a far-range hemisphere for objects that are further away. Each group is sampled separately, resulting in 3 separate AO factors, which are then averaged to get the final AO factor for the fragment. This is important for 2 reasons. 1, it ensures more visually consistent and appealing AO results, with the final factor being equally influenced by objects of varying distances, instead of randomly kind of preferring objects in one distance to another. And 2, it allows us to save performance by sampling faraway objects at lower resolutions. Basically, sampling a high-resolution texture 64 times gets very expensive, but if we think about it, we only need the highest resolution texture to test at depth values that are very close to the fragment position for that very nice accuracy. As these depth values get further away from the fragment's position, we can safely test at lower resolutions to save performance without losing visual detail. In the original paper, this is accomplished with a unique downscaling render algorithm, but I found that using different mipmap levels for the texture worked just fine in my case. For this implementation, I'm using FreeGlut with the GLFW extension wrangler, as well as the gem ipsil helper libraries, which make it a bit easier to load OBJ files, among other things. So let's go ahead and start in main.cpp and just go over the basic flow for how FreeGlut runs in int main. First, we initialize glut, which is essentially a wrapper library to make OpenGL programming more manageable, and we create our window, which our beautiful graphics will be rendered in. Next, we create our callbacks, and this is how we can communicate with OpenGL. We establish callback functions for things like interacting with the window, and most importantly, displaying to the window with onDisplay. This function is called whenever OpenGL wants to draw to the screen. After creating the callbacks, we want to initialize each of our objects and compile their associated shaders. This is done with a class called drawObjectContainers, and does the ugly work of compiling the correct shaders for every object that we want to render into the scene, along with creating and binding textures and establishing their position, scale, and rotation. Once each object is ready, we place it into an std vector of objects called drawObjects, which we will then iterate through when rendering to the screen back in main. We can see a lot of references to the shader compiler class as well, so let's take a look at that. This class is responsible for compiling vertex and fragment shaders for each object, storing its shader information, including a vertex array, into a class called programInfo. ProgramInfo acts as the master class for an object, storing both its rendering information as well as a pointer to the object instance itself. This allows me to track each object in the scene and render their shaders in different orders or with different methods as I please. This class also allows me to actually load .obj files using the gem ipsil helper libraries, bind textures to program information, and create vertex array buffers for each object. Basically, this takes a mesh object and stores its relevant information, including position, normal, and texture coordinates for each vertex, into an interleaved data structure for use when rendering. Shader compiling is where many of the biggest frustrations actually arrived from, as debugging in OpenGL is a really difficult endeavor. There's not an easy way to print to the screen or like debug.log, so locating issues when loading vertex data required a unique debugging process, where I would use an especially simple shader program and just check if I could even get some like red fragment or a point to appear on the screen at all, often using trial and error to triangulate the issue after I was able to get any part of an object to render to the screen. So back to main.cpp. After initializing our program, we'll start running the onDisplay function every time OpenGL wants to draw to the screen. Because I'm using a deferred rendering algorithm, this is going to follow a unique flow, where first I bind a frame buffer to the screen. This means that instead of drawing each object directly to the screen, I'm instead copying its information into a data structure to use later. I then bind a second frame buffer to render the screen space ambient occlusion information, still not rendering to the screen, but storing it for later use. Finally, we're ready to display to the screen. I'm going to draw a screen space quad with normalized device coordinates, which basically means creating a second screen which covers the entire window, and finally, using the information I've stored in my textures, draw the finished scene with lighting, color, and ambient occlusion. This video is going a bit long already, but I want to quickly show off an example of how my shader programs work as well. So let's take a look at the shader I wrote for multi-scale ambient occlusion. This program is compiled by my shader compiler class and runs on a single fragment at a time for the entire screen space quad. Vertex shaders run first and determine the position of a vertex on the screen. That vertex is then passed to the fragment shader, which we have here, determining the color of the vertex. A very simple testing fragment shader might have a single line which simply sets the vertex to a fully red color when we want to make sure it's being rendered to the screen. This shader is rather complex, determining the AO factor for each fragment based on the vertex's stored position, depth, and our sampling variables. This shader takes uniform variables, which are passed directly from our shader compiler script, as well as invariables, like vtex, which is passed from the preceding vertex shader and determines the vertices texture coordinates. The meat of this shader is in this computkernel SSAO function, which loops through each of the three nested hemispheres at different bitmap levels to compute an average AO factor based on random noise sample depth values surrounding the fragment's stored position. This factor is then inverted by subtracting it to 1 and altered based on an SSAO power variable before it is stored back in the gbuffer and ready to use in the final screen space quad. I think that's enough shader talk for today. Thanks for watching, and be sure to check out the original paper linked below.